Munich, and he will give us a talk on OpenGridMap, an open platform for inferring power grids with crowdsourced data. I'm looking forward. The stage is yours.
Hi, so feel free to call me Jose. So basically the outline of my talk, what I'm going to do is I'm going to explain why all of those buzzwords fit together. Yeah, let's turn this on. Right. So, so the outline of my talk, basically I'm going to talk to you a little bit about the motivation, what's the approach we're doing, the benefit, and of course I want to actually, instead of just showing you the cool things we're doing, I want to invite you. I basically came here to ask for your help, because I think this is a very big problem where we need to unite and we need to work together in order to solve. So what is the problem? So this is my favorite German word. Actually, it is a Gedanken experiment, which you can actually use in English. And so you can ask yourself this question. So imagine you go to, for example, my country, Nicaragua, and they ask you to do some study on the power grid or use your technology that you brought from Germany to improve the power system. The first thing you ask is, okay, give me a model. But when I did that, when I went to Nicaragua, I discovered that there was actually no power grid model for distribution lines. And the utility was basically navigating blind. And whenever they had a problem, they had basically to go and look how the situation is and solve the problem. So I asked myself this question, how to simulate the power system of any country. What do we need? Well, if you listen to the talks here, we actually know a lot of things about methods and models. So we have basically that covered. Things are progressing, but that's a problem that we can solve. The other thing you need is computing power. So if you hear this whole big data buzzword thing, you know that we have these huge clusters now that can actually crunch a lot of data. But the thing is, one of the problems that I found is getting actual real data of power grids. It's a little bit of a pain, and nobody wants to give it to you. And if they give it to you, you have to sign an NDA saying that you cannot ever talk about it or publish it. So, so what is the status quo of the power grid data? Well, this is basically how academia sees it. So very orderly, we have these sort of average power grids or these test power grids that we use to test our algorithms. Now, this is how utilities actually want it to be, and a lot of utilities in Germany have been investing in getting geographical information system or GIS. Now, this is not the true of all utilities, especially if you go to third world countries. What you will find is that actually when I asked a buddy of mine in Nicaragua, he took me to a room that looked like this. So there were a lot of plans from the 70s, and the guy who actually drew them already retired, and nobody actually knew what the state of the power grid was. And of course, if you go to India or China or other countries, you can find a situation like this. So if they ask you to repair a fault or solve something and you have to do it there, it's a bit of a problem. So, so improving data quality is a massive task, and I'm not saying we're going to solve it with this problem, but we want to offer an approach that I think has potential. So what is the issue with data? As I said, real data grid sets are not openly available. And if available, most of these data actually are incomplete or inaccurate because, especially at the distribution level, things are changing very dynamically depending on how the system behaves and how you have to repair it. So having this accurate database is a massive problem. And gathering this data is really expensive. So we talked to some utilities, and the ranges are in the millions, of tens of millions of euros. And once they have, if you have to do it, there are two ways basically. If you're with distribution lines, you know that here in Germany we do everything with underground cables. So you have basically to use a metal detector and very expensive equipment and people who know about that in order to map your power grid. The other solution is pretty simple. You just open the earth and see what's in there. Yeah, difficult problem. So we're not the only ones interested in it. There has been a lot of work of power inference based on geodata. Of course, if you have an idea, KIT has always done it first. This is one paper, one of the colleagues that are actually here in Energieinformatik, and they use the OpenStreetMap data set in order to do an inference of the power grid, I think, of Baden-Württemberg. So who knows what OpenStreetMap is? So some of you. So OpenStreetMap is basically something like Wikipedia but for maps. And the reason why it was created, it was because if you use the Google, most of you probably use Google Maps, right? So if you use Google and you make too many requests, you have to pay at the end. And if you make really a lot of requests, these charges can go into the millions. So a lot of people decided we need a free and open database to do that. So that is what OpenStreetMap does, and they basically query the database and look for power tag devices and try to, based on the devices that were mapped, do an inference of the grid. Now, they look at methods and they look at some computer power, but I didn't find, I wrote to them and I asked him, okay, can you give me the data, can you send me some things? And I didn't actually get any answer until now. I'm waiting for the email back. So the other thing that was very interesting where they used geographical data was the DENA study, Verteilung study, which was presented last year here at this conference. And if you look at this study, they have very good methods and computing power, but you cannot really get any data from it. I think they had to sign a lot of NDAs in order to actually do these studies. There is also some other work which uses complex network analysis. And they also use computing power and a lot of methods and models, but they don't actually provide any data for scientists to use. So the goal of our platform basically is basically we have a very strong focus on data and actually making this data available for researchers and anyone who wants to actually use it. So this is the approach. This is the basic workflow we're trying to do. Of course, if you want to have data, first you need to collect it. And there has been a lot of data already collected on OpenGridMap. Now the problem with the data on OpenGridMap is that it's also not 100% accurate because anyone can edit it. And because it is a crowdsourcing platform, most of these people who actually crowdsource this data, they are not electrical engineers. So they cannot tell the difference between a transformer and a generator sometimes. So this is an issue. So in order to solve these things, we are developing some approaches which I'm going to talk about. Of course, we need some verification. We need to do some inference because there are a lot of things that you cannot actually see and map, like underground power lines. And of course, we want to offer the possibility of doing analysis on this data, basic simulations of power grids. This is about the collection. What we have right now is we query the OpenStreetMap database, which is like 630 gigabytes or something. And what we did is we filter everything that has the power tag on it, and we put it on a map. So, and there you can see that there is a lot of data, but the data is disordered, things are not connected, so it's very rough. The other thing is we are developing, we have an app, the first version, which is already working. What this allows you is to go into the field and take a picture of the device. And then this picture gets uploaded to the server. So in this way, we can actually verify, okay, this is actually a transformer. It's not just somebody telling us, okay, I put a transformer here. Because what happens is I did this with OpenGridMap, with OpenStreetMap, sorry, and I went to the place and there was no transformer, so somebody lied to me. So you need some sort of verification for that. The other thing which is quite interesting, I think, is we're doing a lot of aerial mapping. We have a drone, a hobby drone, which are relatively cheap now, and you can actually fly over the area and get basically a 3D reconstruction of an area, and this allows you to make measurements. So you can imagine flying with your drone over the city and actually getting an accurate measurements of what the photovoltaic production is of this area. So these are some of the things that are happening in mapping, and we are exploring these collection approaches. The other thing is verification. So this is actually not very easy to automate. If you get a picture, like the ones we're getting from the phone, from the app, it's very difficult to classify it with some machine learning or things like that because transformers are very different and in every country they're very different. So what we do is basically we have an expert on the loop. So we have somebody, or they call it mechanical torque intelligence, you know. So we have somebody who actually says, okay, this is a transformer or this is a generator or something like that. And you can give it a try. Well, what is the thing on this picture, for example, this thing? Anyone has an idea? You can shout it out.
Transformer?
Yeah, that is a transformer. And that is actually on Ernst-Reuter-Platz in Berlin. And this is one in, I don't know if this is a transformer. I think it's a cable cabinet or a transformer. I'm not sure, probably a cable cabinet. But you can see that the Berliners, they're a lot more artistic with their power grids. So, what is actually a byproduct of this is that I have a huge collection of graffitis now because people tend to do a lot of graffitis on transformers. So let's talk a little bit about inference. So if you can take a picture of things, take the GPS coordinates, it's very easy to map everything you can see. Now the problem is things like underground cables. You cannot see these things. They're buried underground and basically you need a metal detector to find them. So what we're trying is to do an approach based on to do an inference. So what you can see here, this is Garching. Somewhere over here is the Technical University of Munich. And what you see here, these little squares, these are actually the transformers, which are all over the town. So what we do in order to do an inference, you know that each transformer has to be connected to a house. So what we do first is we first partition the area using a Voronoi partition in order to get which transformer has to be connected with which house. Now this Voronoi partition is of course based on the amount of load that a house consumes, or an upper bound on the load that a house consumes. So the next thing is you have to join the dots, right? You have to make the power lines go to the houses. So one way you can do it is basically doing a minimum spanning tree, which would mean that you reduce the amount of power line that you need, which means cost reduction. And it turns out on distribution system, trying to do it as cheaply as possible is a good strategy. So the next thing you can do is, of course, here, this minimum spanning tree is not correct. So one thing you can do is use a diaxtral routing. Basically, you go through the streets, because if you're going to build a power line, you probably wanted to have it next to the street so you can repair it or do some other things. So, but that's on the paper if you want to read more about it. But there's a lot to improve. It turns out that every utility has their own axioms on how they design their power grids. And being so many utilities, you know, it's a very complex problem. So, yeah, I need some input on this. So about the analysis, this is a work in progress. So we're still, that's actually something I want to ask, like which sort of data, in which format do you guys need it, what would be useful for you? So we want to offer this as a service. Now I'm gonna do something very risky and try to show you the portal in the portal. So you can go actually to, oh come on. So you can go actually to OpenGridMap. And this is, for example, Munich. So what you can see here is that a lot of the power devices, they are clustered. And if you zoom out, you can actually see some of the power grids that have been mapped from OpenStreetMap. And if you look into it, you can actually see the characteristics that some people have put into it. So there you see you have 6 cables. It's an operator. The voltage is apparently 380 kV. So what is interesting is that you cannot only do this for Germany. I'm going to go to one of my favorite cities and look at the power grid there. So if you go to San Francisco, you can actually look at their power grid, which might give you some ideas on how this works. Another thing that's very nice, you can have this satellite view, which actually allow you to see this substation, which actually supplies a big part of San Francisco. So one thing you see here is that there is a lot of points mapped, like poles and things like that. But the issue is that these things are not consistently tagged. So a lot of the things that are actually transformers, they are tagged as substations, and many of the poles are not joined together. So for example, you could actually use, that's one of the things we're trying, you could actually use the poles, which are already mapped, in order just to unite the poles that are close together in order to build an inference of the power grid. Also, the distance between the poles basically tells you the voltage, because you have to have this hanging of the cables. So the more distance you have, probably the higher the voltage, because they have to be higher up. So there's a lot of potential in doing this thing. And I want to talk about the benefits, if this works. Okay, so I want to talk about the benefits. Of course, for me the biggest benefit is to improve our research. So sometimes there's a lot of people who do groundbreaking studies, like the Verteilnetzstudie study of Dena. But the problem is it's really difficult to reproduce the results because their studies are based on things that are closed behind NDAs. So that's a big stepstone, I think, in research. The other thing is bring your research faster to application. If you can actually show that your idea works on the network that is right here, or on an inference or the network that is right here, I think this gives you a better argument to actually bring it to application. And the other thing I really like is that you have to go out with your cell phone and map things. So you have boots on the ground research, and that's a picture of my favorite professor. I'm sorry, it's not Professor Schmeck or Professor Jacobson. My favorite professor is Indiana Jones, and you know, he's a guy who he studies history. So he's an archaeologist. So this is a thing that I think has value. We have to look into this power system that we have today and learn from it. You know, as engineers, we're constantly trying to develop new things, but there are a lot of solutions which engineers before us already did, and we actually don't know about it. At least I don't, about all of them. The other thing that I think is cool is to be part of a community. So in my case, I started talking to the power grid guys from Munich and some of the guys that work repairing the cables. That I think has value. We have to look into this power system that we have today and learn from it. You know, as engineers, we're constantly trying to develop new things, but there are a lot of solutions which engineers before us already did, and we actually don't know about it. At least I don't, about all of them. The other thing that I think is cool is to be part of a community. So in my case, I started talking to the power grid guys from Munich and some of the guys that work repairing the cables, and you can learn a lot from those guys. It's nice to organize mapping events and learn from our community, so I want to invite you to become an evangelist. And I will take care of the area of Munich and you can take care of another area. So, of course, if I want to invite you to participate in a project, I need to make some commitments. And the commitments I do is we will publish the data sets and we will publish the models we inferred. And we will keep it free of charge. So I'm basically saying I really need you. I cannot solve this on my own. And let's make it happen. So please, what I want to do is set up a newsletter. So please send me an email so that I can put you on a list and send you updates on the project and ask for your help or ask questions when I have some. So thank you very much.
Thank you very much. Are there any questions? Yes, please. Just wait for a minute. The microphone is coming.
What are the difficult research questions you are or have been working on in this context?
So one of the difficult research questions is about data consistency. So your inference is just as good as your databases is. So you kind of basically have a feedback loop between crowdsourcing data and actually making inference on that. So the way how this data loop is structured is the research question, and especially the inference of the grid. That is, I think, a difficult problem with scarcity of data. Yeah.
So what if I plan a malicious attack and can I use your data to find 3 points maybe in Germany where I should attack and then the whole grid in Germany goes down?
Yeah, so I don't know. I'm not a terrorist, so I wouldn't know how to go about this thing, but I have a slide on that, of course, security. So utilities, they give us a lot this argument that they don't offer their network data because of protection against attacks on critical infrastructure. But to do security through obscurity is really always a bad idea because, you know, we're doing it, and so the question is who else is doing this? If we can do this, who else is doing this? Probably Google, probably some other companies which are not even German. So that's the real question. So we should do it. And of course, this is a tool, so the responsibility is on the user. Yeah. Thank you.
Thank you very much for your interesting talk. I have a question on your Voronoi partitioning. I didn't understand it fully. What is the basis really? Is it simply houses, or is it the population, or I didn't get it?
So the Voronoi partition works as follows. So you have a seed, and in the sense your seed is the transformer. So basically you start growing your space based on the amount of load that this transformer can cover. So basically the coverage of the Voronoi is an upper bound on the load of the houses. So you have a house, and each house has an upper bound on consumption, and we use this in order to do the Voronoi partition. Yeah, but as I said, there's much to improve. So if you have a very good idea on how to do it, I'm very open to listening to it.
thank you very much. It's a really interesting approach to an issue every modeler has difficulties in, I can tell you. And well, we'll see. I wish you all the best.